So here in our Talk the Thought Process series, we're going to be talking about Lewis structures. Lewis structures are a nice, easy way to show how the valence electrons are spread around in covalent compounds. And so what I want to do here is just talk through how we think about making a Lewis structure, and then also when we look at something in series, like things like these here, compounds, we can kind of see how the Lewis structure really works. So here we have C2H6, C2H4, and C2H2. And so in order to first begin making a Lewis structure, our first step is always to count the valence electrons, because the valence electrons are the glue that hold the covalent compound together. And so if we start here with our C2H6, we have 2 carbon atoms and we have 6 hydrogen atoms. Right, so we need to know how many valence electrons there are in each atom. And of course, we're going to look at the periodic table to find that out. So here's carbon, and we see that carbon has 4 valence electrons. We know that because if we count back 1, 2, 3, 4, we will come to a noble gas configuration. And so what that means is that these electrons, 1, 2, 3, 4, are in the outer shell, right? And the outer shell are the valence electrons. They're the ones used in bonding, the glue that sticks the molecule together. Hydrogen is here in group 1, right? And so hydrogen only has 1 electron, and it's just a 1 valence electron. It doesn't have a full shell. That's why it's a valence electron, right? The valence electrons are partially filled shells. Okay, so we'll go back here then, and we'll write down. We have 2 carbons, and so we have 2 times 4 valence electrons is going to be 8, and then we have 6 hydrogens, so we have 6 times 1 valence electron is going to be 6. So our total number of valence electrons in this compound is 14. We're going to draw our skeleton. And so it's kind of an easy one to draw because the hydrogens have to be on the outside. Hydrogen can only make 1 bond with something. Okay, so it's going to have to look something like this, where the 2 carbons are bonded to each other. This line means a bond. And these 6 hydrogen atoms are going to have to be bonded like this, right? That's how we can distribute them around. You can never put the hydrogen in the middle of the molecule because then it would have to make 2 bonds and it can only make 1, right? It can only have 2 electrons around it. Okay, so what I always like to do for a check is to see how many electrons need there be in bonds. And so the way that I calculate that is the needed electrons to form an octet or duet, right? So we've got 2 carbons, and so we have 2 atoms that want to form an octet, and that would require 16 electrons if they were doing it on their own. And we have 6 hydrogens, and each hydrogen wants to form a duet, have 2 electrons around it. That would require 12 electrons if they were doing it on their own, right? And so these are the total number required to form octets and duets. And so what we see is we only have 14 electrons. And so what that means is the electrons have to be shared between the atoms. Otherwise, these atoms cannot obtain their octets or duets. So we can see how many need to be shared by subtracting. What's the difference? 28 minus 14 equals 14 electrons shared. And every bond has 2 electrons, so if there's 14 electrons shared, 14 times 2 is equal to 7. There are 7 bonds. And so if I count my bonds, these lines here, 1, 2, 3, 4, 5, 6, 7. There we go. We've got the 7 bonds. Now we always want to check our Lewis structure for number of valence electrons. So we'll count them all. Remember, 2 in each bond. 2, 4, 6, 8, 10, 12, 14. That matches the number of valence electrons we said we wanted. And then we want to check each atom for octet or duet. So this carbon has 2, 4, 6, 8 electrons around it. This carbon has 2, 4, 6, 8 electrons around it, so that's good. each of these hydrogens has 2 electrons around it in that bond, right? So that one looks good as well. Okay, so now when we move to the next structure, C2H4, what's different about this one? Well, it looks like we have fewer atoms, fewer valence electrons. But again, we can go through the same process. There are 2 carbons, and they're in group 4, so we have 2 times 4 is equal to 8 valence electrons. There are 4 hydrogens. Hydrogen is in group 1, so each one has 1 valence electrons. That's 4, and so now we've got a total of 12 valence electrons. Okay, again, we're going to make our skeleton, and the only way that we can do it is like this, because the hydrogens have to be on the outside. Okay, and then if we do our calculation to see our needed electrons for forming octets and duets, again, we have 2 carbons. They each need 8 electrons around them to have their octet. That's 16. And we have 4 hydrogens. They each need their 2 electrons around them to have their duets. And so the total there is 24. Right, so they need 24 to be happy. There's only 24 or 12 available to them. So we have to take the difference to see how many they need to share. 24 minus 12 is equal to 12. So they're going to be 12 shared electrons. And that means there are going to be 6 bonds. So far we have 1, 2, 3, 4, 5. To have 6 bonds, we're going to have to put the other one here in between the 2 carbon atoms, but you can't have more than 2 electrons around your hydrogen. So does this look like a happy molecule? We've got 2, 4, 6, 8, 10, 12 valence electrons, so that checks out. And then each carbon, 2, 4, 6, 8. This one has 2, 4, 6, 8, so those are happy. Each hydrogen again has 2. Right, so that checks out to be a happy structure. Right, so now if we go to the next one in this series, we've got C2H2. So with C2H2, fewer atoms, fewer valence electrons. Again, we have 2 carbons, and so each one has 4, being in group 4. That's 8 valence electrons. We have 2 hydrogens. Each one has 1, and there's 2 of them, so there's 2 valence electrons. So total we have is 10 valence electrons. We've got to put this one together in the same way with the carbons in the middle, and then there's only 2 hydrogens, so I'm going to put 1 on each just to be fair, like that. And then I can calculate again how many needed electrons for each atom to have an octet or a duet. There's 2 carbons. Each of them needs 8. 2 times 8 is 16. There's 2 hydrogens. Each of them needs 2. 2 times 2 is 4. Total needed electrons, 20. They need 20, but they only have 10. So that means they have to share 10 of them. 20 minus 10 equals 10 shared electrons. If we have 10 shared electrons, and there's 2 electrons in a bond, then that means 5 bonds. Here we have 3. 1, 2, 3. The only place we can put the other 2 is right there. Okay, so let's do our check. 2, 4, 6, 8, 10 electrons we've used, and there were 10 available as valence electrons. Carbon has 2, 4, 6, 8, an octet. This carbon has 2, 4, 6, 8, an octet. This hydrogen has a duet. This hydrogen has a duet. So that also looks like a happy molecule. So sometimes, you can sit and stare at the atoms and count up the electrons and figure out how to stick them together, and it'll certainly become more intuitive as you practice more. But when you get stuck, you can do this simple calculation. Count the valence electrons, count the number needed to form an octet, take the difference, that's going to be the number of electrons that need to be shared in bonds. From there, you know how many bonds, and then when you put them in, you're going to see that everything is pretty happy there. All right. So there we've drawn some Lewis structures of 3 molecules in a series to show how valence electrons are distributed, to show how the atoms need to share in order for them to be as happy as they can be, which is for the nonmetals to form an octet, except for the hydrogen to form a duet.